Okay, hi everybody, Professor Sebastian again. Welcome back to our Calculus 3 class notes. We're in the middle of page 58. Here in section 14.5, section on partial derivatives, or chapter in partial derivatives, but in section 14.5. So, gradients and tangents to level curves. If a differentiable function, f of xy, has a constant value c along a smooth curve, parameterized as x of ti and y of tj. So what it does is it makes the curve part of a level curve of f. Okay, so actually what we're talking about is a level curve. Then f of x t and y t equals c. Differentiating both sides of this equation with respect to t leads to the equation. Okay, so if you differentiate this side, you got to use the chain rule. Partial of f with respect to x, dx dt, plus partial f with respect to y, dy dt. Derivative constant is 0. So what is that? That's the gradient vector dotted with dr dt. This is the derivative of r with respect to t. So what we've said is if we have a level curve of f, then the gradient of f is normal to the tangent vector on that level curve. So it's normal to the curve. Now normal means perpendicular, right? So the gradient of f is perpendicular to level curves. So what's the tangent line to a level curve? The tangent lines to level curves are therefore normal to the gradients. So the line through a point p naught of x naught y naught normal to a vector n, let's say that vector n is ai plus bj, has this equation. Okay, so that's called the point normal form of the equation of a line. Right? Thus, if n is the gradient, which it is in this case if we're talking about level curves, the above equation gives the following formula for the tangent line to a level curve. Partial of f with respect to x, evaluated x naught y naught times x naught y naught, times x minus x naught, plus partial of f with respect to y, evaluated x naught y naught times y minus y naught equals 0. So we have a nice equation for the tangent line to a level curve of any function. Uses the gradient vector, uses the fact that the gradient vector is perpendicular to the derivative of r, with r parameterizes that level curve, which is tangent. Okay, so example 54, let's find an equation for the tangent to the ellipse x squared over 4 plus y squared equals 2 at the point minus 2, 1. So we're going to recognize here that this ellipse is a level curve of z, which is f of xy, which is x squared over 4 plus y squared. So the gradient of f is x over 2i plus 2yj. Gradient of f at the point minus 2, 1 is minus I plus 2j. So these are your A and your B in your equation for the tangent line. So it's this minus 1 times x minus x naught, which is x plus 2 times y minus 1 equals 0. And you can simplify that and put it in standard form or in slope-intercept form, whichever a problem calls for. So really quick before moving on to the next page, let's look at the algebra rules for gradients. The summation rule, if I take the gradient of f plus g, I can take the gradient of each separately and add them together. Same with the minus, of course. If I have a constant times the f, I can just pull the constant out front. Notice these are very similar and actually just like our typical rules for taking derivatives. The gradient of f times g, I use a product rule. F times the gradient of g plus g times the gradient of f. And for the gradient of f divided by g, I use the quotient rule. Low d high is g times the gradient of f minus high d low is minus f times the gradient of g divided by the bottom squared, so g squared. So the rules work the same for gradients as they do for regular derivatives.